Hi everyone, welcome back to the channel. So today I thought I'll make a quick follow-up to our previous video on VCO design. So what I want to do in today's video is just to show you how you can design the inductor that you need and kind of make it more realistic. And then in the next one, we'll look at follow-ups on how you can integrate it into the system. So let's begin. This will be a quick video because a lot of the material required for this was already covered on my channel before. So if you go to the playlist on millimeter wave integrated circuits, we will use basically videos that we've done before. So this is kind of follow up to this one, cross-coupled VCO design, which of course makes use of several videos before, right? But today, especially, we will be using some material from this video, the back-end applying metal and dielectric extraction video, and also sort of the first one in this series, which is a parametric design of on-chip inductors and transformers. Okay, so kind of let's get started. So we'll be taking off from our last design, which is this one. And in this case, I just want to use continuous tuning. I don't need the discrete tuning, so I'm just going to delete this part. And because I've deleted that, I need to add back some capacitance, right? So I'll call this C1, and then we'll add back. Okay. So if you don't know what all of this is, you should definitely watch the video before this because that's very important. Okay. So essentially, we have our MOSFET actors here. We have some fixed capacitance, and we have our inductor and the equivalent resistance. Actually, I don't want to make changes to this one. Let me make a copy of this. A6. Okay. So let's do that again. So what we're trying to do now, what we want to do now is we want to kind of bring it to 10 gigahertz and see how much continuous tuning you can get with something like this, right? So once again, we open up ADE and then we can load up our session. And let's run it and see what we get. So let me just organize this a little bit. So, so we need to pay attention to the V peak to peak, the current, the figure of merit, and the frequency. Right? This is what we did earlier as well. So we see that the frequency has kind of dropped. That's because the capacitance needs to be around maybe 100 femto. Right, the 270 was before we added the varactors. So with the varactors, actually no, it should be 270 femto. That's my bad. And now that we removed those discrete tuning caps, we can reduce the number of fingers again because we don't need to overcome that much loss in the tank now, right? Okay, so this is pretty good. It's close to around 10 gigahertz. So for example, if I make this 0, then it should go from around 9.7 to 10.3 or so, right? Around 10, that's fine. Okay, and the figure of merit is nice. So this is sort of the design that we'll start with and try to just make the inductor more realistic, the real inductor, right? So what we can do is we can kind of delete this. So let me move these guys out of the way. Delete all of this. And then I'll put it in the queue. And 1, 2, 10 gigahertz. There. Here. So let's add the Q of around 8 to 10. I know we chose 8 kind of when we designed this initially, but 10 is also fine. Okay, L1 of 590 pico. Okay, let's see what we get. Okay, so it's around 10 gigahertz, right? Okay, so maybe what we need to do now is to go and see how do you make an inductor like this in HFSS, and that's what I've kind of done here. If you don't know how to design this, I would highly recommend you watch this video where I cover exactly how to design it and how to make it parametric. And the only thing I've kind of added to that, to the design in this video, is sort of this bias line in the middle. And that's also fairly straightforward to do. So in that video, I used different dielectric and metal values, whereas in this one, you have to use the one for this PDK. So to do that, what you can do is you can go into this one, this video, watch this one, and in that we extract exactly the dielectric and metal properties of all the layers. So these are all the metal layers, and these are all the dielectric layers of this PDK, the GPDK. And since I've already done this, I'm not going to do that again. Okay, so essentially this is our trial inductor. Okay, so let me actually make a copy of this, show you what I've done. So these are all the dielectric layers that we've extracted. This drawing of this inductor is covered in the first video on this channel, on this series. So if you want to find its inductance, you need to kind of get rid of this this piece here. So I'm actually going to delete this, right? So that it's just 2 ports, and then you can use the Y parameters to kind of extract the inductance, which I also show in that inductance video. So let's simulate this and see what it looks like. Okay, so the inductance is, you can add a marker. 10 gigahertz is around 1 nanohenry or so, right? And this equation that I've used here is in terms of picohenry. Right? And one thing to keep in mind is when you want to extract S parameters to use in cadence, you need to make sure the sweep goes down from 0 gigahertz because you want the DC as well for the bias lines. So since this inductance is going to be part of the bias as well, you need to make sure you simulate it from 0. Otherwise, that can lead to issues. Okay, so the rest of the setup is already covered, so I'm not going to go into it. But essentially, the inductance is around 1 nano, and quality factor is around 10 to 12. And this is for 2 turns, where the diameter is around 150. Right? That's quite big. So if you measure, for example, this is around 260 microns. So that's quite large, right? So what we would like to do is we want to actually make this a little smaller. So to do that, what I've done is I have kind of made it into 3 turns. And if you really understand how I drew this in that video out here, then it's fairly straightforward to actually make it 3 turns as well. So with 3 turns, we can reduce the size a little bit. So it's around 195, so it's around 200 microns, which is not too bad. Still fairly large. So this gives us about, I already simulated this, about the same, so around 200, around 2 nanohenry. It's actually not about the same, actually, it's quite a bit larger, right? Yeah, so this is around 1.1 nano. This is almost 2 nano. So the reason I did that is because I would like to actually have a higher inductance, so about 950 pico, and the lower capacitance of about 100 femto. This is actually the original inductance that we started with when we started this design. So this takes me from around 10.2 to 800 milli at 0 volts. And when you use 800 milli, you should get around 9.6 or so. So 9.6 to 10.2, right? That's good enough tuning range. Okay, so since each inductance is 950 pico, if you look here, essentially these two will be in series with a single VDD. So let me actually do that. They should do the same results, of course. It's no different, right? Okay, so since we need about 950 pico on each inductor, you really need about 1900 pico for the whole thing. And that's kind of what we have here. So that's what this is. And of course, you have to play around with these values. For example, you can make this 100 and simulate that, or 150 and tune it a little bit. So how to automatically design based on certain parameters, that we will look at later when we look at interstage matching. In this case, you don't really need that. This is fairly straightforward. You only need to try a couple of values and see what works for you. So that's what I've demonstrated here. So this is what it looks like with the bias line connected. So for example, bias line is out here. I come down to a bottom metal layer. So for example, M11 is the metal layer in which I'm doing my inductor. M10 is the metal layer for the transition. And then M8 is this bottom metal layer that I'm using for the biasing. Although I've kind of connected it to M11, I assigned the same metal layer because it doesn't really matter. It's just a small piece of metal. But yeah, that's what I'm doing here. So that's what the topology looks like. Okay, with this simulation, you can't find the inductance because you can't really use the Y parameters of just a two-port network. It's a three-port network. So just make sure that you keep that in mind. So this is just to extract the S parameters, right? So to extract S parameters directly, one thing you can do is you can go to design settings, export on completion, and then put your folder here basically where you want to export, and then export it that way. Okay, so once you do that, then just go ahead and run the simulation. I've already done that before. So let's go ahead and look at it in cadence. Okay, so now we can delete this. Delete, no, this is the older one. Change this. Yeah, this is the one. So now what I'll do is I need to add a port. 3 ports, say browse, and then you want to go to the design that we just simulated, which is World 2, and we'll take the latest one. It's a 3-port. Make sure this is a 3-port S parameter file. Then we need to put it down. So port 3 is the DC port. Connect these two up, and we need a reference ground. Okay, there we go. All right, so let's run this and see what we get. Okay, so it's pretty close. really good figure of merit actually, around minus 186. Peak to peak is 480, so that's also good. And the current is also more than slightly above 1 milliamp, right? So that's also pretty good. So let's just check the tuning range from 9.87 up to 10.4, right? So that's good. That's a good tuning range. So we really want it about 9.75 to 10.25 or so. That's what we're going for. Okay, so to get that, what I will do now is I'm going to replace these caps with some non-ideal caps. So these ones. So that's one. And okay. I also want to change the parameters. So I'll call this min2, min2. Let's save this. So we'll say this is maybe 1 micron and about 50 of them. So you can find out exactly what the value needs to be, but in this case, I'm just trying this. Let's see what happens. Okay, 10.4. So the way I like to do this sometimes is that I can set this to the center, 400 milli, and then see what we get. So try to center it at around 10 gigahertz, basically. It's 10.3, so I need to increase the capacitance a little bit. So let me actually just tune this a little bit and I'll come back. Okay, so I just have to change it to 55, just a few minutes, couple, 1 or 2 minutes really. And now you can see when mass cap voltage is 0, it's 10.24, and this is 800 milli. It goes from 10.24 to about 9.72, right? So that's about half a gigahertz. And essentially, we'll take this half a gigahertz and then we'll design a 3-stage doubler. So 3 doubler stages essentially to go from 10 to 20, 20 to 40, 40 to 80, right? So the goal is to be around 80 gigahertz, let's say for automotive radar band, right? But of course, you can take this to any band that you like. And even the phase noise is pretty good. It's around minus 183 to minus 185, the form. And you can see at 1 megahertz offset is less than minus 105 dBc per hertz. That's pretty good. So keep in mind that this should be less than the threshold voltage, and this should be slightly higher than your bias current, right? Which is 1 milliamp or so. So, okay, this is a pretty good design. Now what we need to do is we need to take the layout from HFSS and bring it to cadence. So let's do that. So let me actually just quickly save this. I can close this. You can also close this. All right, so now that I've designed this in HFSS, of course, you can also design inductors using other tools like EMX. The only reason I don't really prefer that is that when you go to higher frequencies, let's say higher than 30 gigahertz, close to 100 gigahertz, or definitely above 100 gigahertz, EMX is not that accurate. So HFSS is still the most accurate solver. So becoming familiar with HFSS is very, very useful, especially if you want to do antenna design, things like that on chip. So, and most importantly for millimeter wave and terahertz designers, right? So getting to know how to use this correctly is very important. For example, in this case, these ports that we've added have parasitic inductance, which we have not removed yet. And we'll deal with that in future videos. Right now, it doesn't really matter because it's very small at these frequencies. It doesn't matter, but something to keep in mind, right? So, okay. So we need to export the layout of this guy and import it into cadence. So how do you do that? You can select objects, select all the objects, say modeler, export, choose GDS2 here, and then you can call it whatever you like. So let me actually go to a folder that where GPDK. It is HFSS. HFSS is fine. Okay. So I'll say Inductor GDS, and then hit save. You can export all layers, that's fine. And we go to Library Manager, go to YouTube, the video what we just made. Create a new cell view. Six. Excel. Hit OK. It opens the schematic. Okay, so let's import the inductor. Import stream, and this is the one that we just saved, I believe. Inductor GDS. I think this is the one. Anyways, hit OK or open, and then select the library you want it to be in. In this case, it's this. You can leave the top cell blank, that's fine. Translate. Close this layout. So this is the GDS file. And you can see it's here. Okay, obviously the layers are not going to be correct. They're going to be sort of random based on some layer mapping that it wants to use. We need to change that. So that's the first thing. The second thing we need to change is that this is not going to be on grid, obviously, because in HFSS it's not doesn't know anything about grids, right? So when it makes these bends, especially, the grids will be off. So to get the right grids, what I usually do is I kind of redraw on top of this. So let me show you how. So this is VR1. It shows VR1 to make the M11 layer. Go to routing, select M11, Shift P to draw polygon, and then I'll draw a polygon on top of this. And make sure you're in the right snap spacing, right? So here I've chosen 0.1 rather than 5 nanometers because it doesn't really matter. And for diagonals, if you hit E, you need to make sure these are diagonals as well. Okay, so I'll just go about and make these polygons. There's a little bit of error, of course, but that doesn't really matter. It's very, very small. Okay, it's done with the first one. Okay, there we go. Right? That's the first one. So basically you go ahead and I usually go ahead and draw all the layers like that, including the vias, transitions, and so on. And I've already covered layouts before in other videos. So I've done this one. We did a little bit of layouts, but most importantly, this one, Introduction to Layouts and Cadence, right? So anyways, we'll redo some of the layouts again when we do the full circuit. So I'll do the layout for the entire thing, including this inductor, in the next video, where we'll talk about how to properly design transitions in HFSS between between different layers. So how to accurately model transitions between transistors and the passives. So the front end of line, which is the transistors, and then the passives like inductors and so on. For example, in this case, how do you actually connect this to your transistor, right? Can you leave it just like this or not? How to do it accurately? So all of this we'll cover sort of in future videos. But essentially, in this, I just wanted to show you how to make the inductor, how to design it for a specific value of inductance and Q, how to make the layouts in HFSS, most of which was covered earlier, and then how to bring that design from HFSS to cadence layouts, and then how to do the layouts such that they are accurate and on grid. So that was essentially what I wanted to cover today. It's a short video compared to at least the other ones. So in the next one, we look at the layout of this entire oscillator in one layout, and we'll look at how to do that more accurately, and then we'll go on to doubler design and then future videos. Okay, hopefully you're excited about that. So thank you so much. I'll see you in the next one.